Finally, we are ready to show that there are infinitely many prime numbers. Now, the idea of this proof is the following idea, and I don't recommend memorizing the proof. I just recommend understanding how the proof works and being able to kind of repeat it or mimic it, but don't really memorize everything word for word. The idea behind the proof is this. We're going to suppose that the prime number set is finite. So basically, we're going to suppose that there are, 10, 20, 30 prime numbers, however many you want, but there's finitely many of them. And what we're going to do is take all the numbers in the list that we just created for the prime numbers. Since the list is small, we can multiply all the numbers. And then we can add 1 to that number. So by the theorem 4.3.4, this number must be divisible by some prime number. Every number in the world is divisible by a prime number, either itself or something else. But by the proposition 4.7.3, this number is not divisible by any of the primes in the original set. So there must be a prime that is not in the set that we had, which is impossible because our set was supposed to be finite. So how could there be an extra prime number that wasn't there previously? So basically, that's the idea behind theorem 4.7.4, and I'm gonna present the details next. And we know that this is a true statement, so we are going to be proving this statement. Now keep in mind that this statement is not an if-then statement, so I cannot prove it by contrapositive method, but I can prove it by contradiction or directly. It will be very difficult to prove this statement directly because I would have to basically find every prime number out there in the universe, and that's going to be very, very difficult. So the only method that's left at this point in time is to do a proof by contradiction, and that's the plan for this problem. So we're going to start by supposing not, meaning we're going to suppose that this statement is not true, that the set of prime numbers is actually finite. And that's supposed to lead to a contradiction. Now, let's see how we derive this contradiction. Since the set of prime numbers is finite according to this assumption, there must be a greatest prime number. Let's go ahead and call that biggest prime number in the list, capital P. And it follows that we can now organize our list of prime numbers from smallest to largest. So we can put them in order. We know the first few are 2, 3, 5, 7, 13, 11. We can organize the list in order from the smallest integer that is prime to the largest integer that is prime according to our assumption, which is called capital P. Now we can create a number n that is the product of all of these integers in the list. Remember, they're all prime, so I can make a product of all of them, and at the end I can add a 1 to it. Now, I know that this n is bigger than 1, obviously, because I'm multiplying 2 times 3 times 5 times so on and so forth times capital P, and then adding 1. So for sure it's bigger than 1. So there must be some prime number that divides n. And that prime number I'm calling q. So there's a q that divides this list plus the 1. And keep in mind that q is supposed to be prime. So if q is prime, then q must come from the original list of prime numbers. But by definition of divisibility, this would imply that q divides the product of all these guys, because it's one of them. So for sure it's going to divide the product of them. And because q divides capital N, q is going to divide all of these guys. So wait a second. How could q divide 2 times 3 times 5 times 7 times all the way to p, and then divide the next integer as well? In the last problem that we proved, we showed that a prime number cannot divide a and a plus 1. If the prime number divides a, then it will not divide a plus 1. And that's our contradiction. So to be clear, how is the contradiction showing up? The contradiction is showing up because we are basically saying that Q divides the product of 2 times 3 times ... times all the way to capital P. And we also said that Q divides the N. But in the previous theorem, we said that if Q divides the product, then it cannot divide the product plus 1. But we're assuming that it divides the product plus 1. So, there's something wrong with this whole picture. And that's how we're getting our contradiction.